Hi, this is Grover with Blue Collar Codes, the Quick and Dirty, episode 19, the first of the intermediate Python series. Going to give a high-level overview of Big O notation and, in the very least, the first three, constant, logarithmic, and linear. If you wish to follow along, you can find episode 19.py in the GitHub repository, which is linked in the video summary. So Big O notation is a way to rank your algorithm, which is basically just a function or a pair of functions that are doing some kind of action or work on a data set or an input. And so this is a way to rank yours and give it a ratio designation that has to do with the size of the input and how it relates to the time it takes to complete the function. Meaning, how does the time it takes to run the function relate to the size of the input? Is it increasing? Does it matter? Is it exponential growth? And one of the things that I have here for you is a chart that I took from a data structures and algorithms book for Python because it outlines it visually for you to showcase how the time increases based on the size of the input for each of these different types of Big O notation designations. So you have constant, which means that it's not affected by the size of the data set. So that's the best case scenario in that you can have an infinitely large data set and you'll still have the same time it takes to complete. And then you have logarithmic, which is the next best, and then linear, which is then a lot larger, as you can see. You have these two and then here. And those are the ones that you really want to strive for. And then the other ones are things that are basically not as great for large input sizes. You have linear logarithmic, you have quadratic, cubic, and then exponential. So to dive into some examples of how the code itself relates to these Big O notations, we'll start with the constant time complexity. So constant time is basically the same as pulling up an index of a list. Constant time means there is not going to be any looping structures, nested looping structures. It is simply accessing, assigning, or performing an action that doesn't require any looping. That's almost the basic simple way to understand is that there's no looping when you have constant time. So the next example is logarithmic time complexity, the next best efficiency. And I'm going to go a bit into this one and step through it and explain it just because binary search is probably one of the biggest things you're going to want to know if you're going to pursue this career or pursue knowledge in programming languages. So I'm going to go ahead and run the debugger here because I want it to stop here and so we can step through it. And so what binary search does is first, it only works in certain situations. So there has to be, say, if it's finding a value in a sorted list. So I chose here 10, which is the worst case scenario. So either 1 or 10 are going to be the worst case scenarios for the time complexity on logarithmic, meaning it will have to go through and parse the entirety until it gets to the last possible loop until it finds the value. And what it's doing here is it's basically finding a middle index by dividing the left and the right, which are index values for the far left and the far right. And then it's comparing this middle indexed value, and in this case it's 5, to the target. And so 5 is less than 10, which means, and since this is a sorted array, that means that now what this algorithm does is it changes the left index value to now 1 past the middle value, and then it starts again. And it divides the remaining amount that we're going to check, checks the middle value again, sees that the 8 is less than, and then it repeats that until it finds out, finds the index value for 10. And so we'll step through a few of those to see here how the left and right start as the 0 index value and then the right is the 9. As we step through it, it's going to assign the middle as the 4th, which is the 5, the 4 index value. It's going to see that the target did not equal 5. It's going to say that the middle value was less than, so now it's going to alter the left-hand marker and make it 1 past the middle. As you can see here now, left updated to be 5. And now we're just checking from the 6 to the 10. And so now it's going to repeat that process, find another middle value, which becomes 7, the 8, compares it, finds that it's still lower, and so now it alters the left-hand marker again to now the 8th. And now it's going to continue until it finds that value, and it will return the 9. The reason why this is a good time complexity is that it's really trimming down the size of what it has to search through to find that index value at each iteration. The next and last one that I'm going to go over is just linear time complexity. And that basically means that you're going to be looping through the entirety of the values here. You're not going to be doing it twice, you're just going to be going straight through once. That's linear time complexity. And you're really always considering the worst case scenario. So let's say for this instance, it would be trying to find the 10 in this and starting at the 1 value, or starting at the 0 index place and trying to find the 10 at the last index place. So you're going to start here, see if it's your target value, then you're going to move to this, see if it's your target value, and so on and so forth until you actually find it, but it had to go through the whole list to do it. And so you can see if that's an exceedingly large list, having to do it linearly would be relatively cumbersome. And the rest of these get a bit more complex, but they're basically start to nest features. If you're nesting or performing multiple search algorithms within the same algorithm, then it starts to get more complex. And we'll go over these at a different time, but it's just good to be aware that they exist. So again, this was Grover, Blue Collar Codes, episode 19, just giving a brief overview of Big O notation. Thanks for joining. See you next time.